Okay, everybody, I want to go over yesterday's molar heat and specific heat review, starting with the definition of the molar heat of fusion. So amount of energy required to melt a mole of a substance. So remember, something like water, we use the triangle H, delta H for water is 6.009 kilojoules per mole. So remember what that means is that this energy is flowing from something like a stove or the environment into the substance like water. And also remember that we learned that that number is actually from a calculation. Q equals mass times specific heat times change in temperature. So that gizmo that you were doing was focusing on this, which is called specific heat. Specific heat. So we've learned about this molar heat and this specific heat. But to come up with a number in kilojoules, we have to actually calculate that as well. So you were supposed to Google some molar heats for specific substances. So I have water there, but you could have come up with two of your own for molar heats. And then use a sentence explaining what the molar heat literally says. So I just used water. It takes 6.009 kilojoules to melt 1 mole, which is 18.02 grams of ice. Okay, so now you're calculating a molar heat, right? Molar heat is just kilojoules over moles. So they gave you a number in joules, so we can convert that to kilojoules, 4,000 joules. So 1,000 joules on bottom, 1 kilojoule on top, because a kilojoule is 1,000 joules. So we're just dividing by 1,000. And that's 4 kilojoules. So 4 kilojoules goes over 2.5 moles. We end up with 1.6 rounded to 2 digits, kilojoules per mole. So that's the molar heat of fusion for some substance. It doesn't tell us what it is. We just know that that's its molar heat of fusion. It takes that much energy to melt 1 mole of it. Okay, molar heat of vaporization is similar. It's still a kilojoules over moles number, except it's the amount of heat required to vaporize a mole of a substance. So water, we talked about this in class when we were actually in class, 40.79 kilojoules to vaporize 1 mole of water. You could have come up with 2 on your own. And write a sentence about one of those. So it takes 40.79 kilojoules to vaporize 1 mole or 18 grams of water when the water is at its boiling point. So remember, it has to already be at its boiling point for this number to be true. We're not talking about the heat to get it to its boiling point. Another solving problem, so we have 18,000 joules and we have this many moles. So we're going to convert that, 18,000 joules. We're going to turn it into kilojoules. So 1 kilojoule is 1,000 joules. So 18 divided by 1,000 is just 18 kilojoules. We're going to put that over 0.0634 moles. Okay, and then neither of those units cancel out, so we have 284 kilojoules per mole. So that takes a lot of energy. Whatever this is, takes a lot of energy to vaporize a mole of it. Okay, so the backside was about specific heat. So let's go back to this. So we're talking about CP, or specific heat, which is how we get these kilojoule numbers. It's calculated. So what is specific heat? It's the amount of heat energy required to raise a gram of substance by 1 degree Celsius, or the amount of heat lost if it's cooling down. Okay, so you're supposed to find 3 different substances. So I put water in there again just because it's so common and important. So it takes 4.18 joules to raise 1 gram of water by 1 degree Celsius. Ethanol takes much less because it has weaker bonds. Lead takes even less, 0.129 joules per gram degree Celsius. Doesn't take very much energy to heat up most metals. Okay, so making a sentence for lead. Lead requires 0.129 joules of heat energy to raise the temperature of 1 gram by 1 degree Celsius. Okay, now we're doing a solving problem. So what is the specific heat? So since the original equation is Q equals M times Cp times delta T, we're asked to solve for Cp. So how do we solve for Cp? We're going to divide by M and delta T. M and delta T. So it'd be Q over M times delta T. Cp equals Q over M, times delta T. Okay, so let's find those numbers. So there's Q, that's energy, right? 4,000 joules, 4,000 joules. Our mass, 16 grams, 16.0 grams, and our delta T, so it heated up by 50 degrees. That's a change in temperature, so that's 50 degrees. Okay, so we put all that together, and again, none of those units cancel out. So we have 5 joules per gram degree Celsius. Okay, so let's say the substance from number 6, let's say it dropped in temperature. So it went from 50 down to 15. So that's a change in temperature. That's a delta T. How many joules of energy did this substance lose? So we're asked to solve for joules. That's Q. So we're just going to multiply all of these together. So it's the same substance as before. The mass was 16 grams. There it is. So that's our mass. Our change in temperature this time is 50 down to 15. That's a 35 degree change. And our Cp, which we just figured out, is 5. So we're going to string all those together, 16 times 35 times 5. And that equals 2,800 joules. If we wanted to convert that to kilojoules, we could just divide by 1,000. That would be 2.8 kilojoules.